So welcome back for more lectures. So this is lecture number 9. And it's going to be the last lecture. All right, last time you remember, okay, we derived the Lorentz transformations for the magnetic field B. And the way we did it was to, in fact, remember that both the electric field E and magnetic field B are contained in this second rank tensor F mu nu, which carries two indices. And we also make use of the fact that tensors they transform under Lorentz transformations just as products of vectors. And we know how the vectors transform. Therefore, we know how the second rank tensor F mu nu transform. And that's how we manage to arrive at the following, namely that the x component of B in the prime frame is equal to x component of B. By the way, x is along direction of relative motion, so I will call sometimes the x direction to be the longitudinal direction. In that case, then the yz components will correspond to the transverse directions. The transverse components of B, of course, refer to y and z components, involves two directions. That's why I have to use a vector notation and transform in a slightly more complicated manner. In particular, in addition to B in the prime frame, there's also this term, the electric field E, in the prime frame in this expression for the B prime. All right, next, of course, we should also see how the electric field E transform under Lorentz transformations. Now, things are not as easy at first sight because of the fact that the electric field E involves the CF component, one of the instances in the tensor being 0, the time component. And in particular, if you take a look at I being the x direction, then it will be F01. But the CO1 directions transform non-trivially under Lorentz transformation. See? The 0 and 1 direction transform non-trivially, unlike the transverse directions. So things will appear to be more complicated in order to derive the Lorentz transmission laws for the electric field E. Luckily, we remember the nice transformation known as duality transformation. So we can make use of duality transformation to write down, in fact, the E prime and the transverse part and E prime, the longitudinal part, without too much work. Starting from these two expressions. All right. First, let me start with the longitudinal component of B. And the duality transformation, you remember that E goes into CB, and B goes into minus 1 over CE. So the B goes into minus 1 over CE. Let me forget about this factor. So essentially, in that case, then this equation will be translated into the x component of E is equal to the x component of E. So the longitudinal component of the electric field E, just like the longitudinal component of magnetic field B, is invariant under Lorentz transformation. Next, we do the same thing here. B goes into 1 over C, E with the y side, and do the same thing here. And for E, goes into this one. Then we will arrive at E prime, the transverse direction, to be equal to gamma. You can do the algebra very quickly. Plus V cross B. By the way, I should also remind you that V cross B, of course, has a non-zero longitudinal component. But the component of this cross product, V cross B, is identical to 0. Because V is along the longitudinal direction already. So its cross product with anything else would be 0. Okay. It's nice to remember this. Whenever you talk about longitudinal component of a cross product of this V is along the direction of longitudinal component, that vanishes. All right? With the help of these two equations for transformation of the electric field E, now we're going to do something wonderful. You remember that we talked about magnetism as a relativistic phenomenon, namely that magnetism arises from electrostatics and special relativity. And we did it for a special case, a particular situation. Now we are going to generalize the whole discussion to the following, namely that you remember that in the Lorentz-Force law, there is this piece involving the electric field E. And there's also this piece, V cross B. Let's assume that we already know about the effect of electric field E on a charge. And let's say that we do not know what it is, and we would like to derive it, this term, in the Lorentz-Force law. Now we can do it with the help of the transformation laws for the electromagnetic field. In particular, these two equations. That's how it can be done. All right? So let's consider a particle with charge Q moving with velocity V in the unprime frame, which I will call the S frame. In the presence of an electric field E and a magnetic field B. And we would like to derive the Lorentz-Force law in this frame. The way we're going to do it is to make transformation from the S frame to the prime frame, which I will call S prime frame. In the S prime frame, the charge Q is at rest. Okay, let's see what kind of force would be exerted on the charge Q in S prime frame, knowing that we'll make a Lorentz transformation to go back to this original unprime frame. So this is the tactic. All right? So that in the S prime frame, we will be in the presence of electric field prime, magnetic field B prime field. But since the charge Q is at rest, so that it will feel only, from our study of electrostatics, there will be only the force due to this electric field E prime. And we know that F prime is equal to Q E prime from a study of electrostatics, which I assume we know already. All right? And for the left-hand side, we have force in the prime frame. Force, of course, is the rate change of linear momentum. So this is equal to E P prime by D time. What's the time? In this prime frame where this charge Q is at rest, and this force is force acting on Q. So the proper expression for time, this expression, would be the proper time, d tau. Proper time, you remember, is the time as seen in the rest frame of the system. And the system here is, the charge Q. So that in fact it's dP prime by d tau. This is equal to Q E prime. And let me consider, the transverse component of this equation and the longitudinal component of this equation separately. And I would, so that means that I'll be interested in to consider this three-dimensional, three equations. First of all, talk about this transverse part, which involves the y and z component, and then the longitudinal component. I would do the calculation explicitly just for the transverse part. And just to save time, you can also do the one for the longitudinal part without too much difficulty, especially with the help of my lecture notes. All right, so let me consider this for this discussion. The transverse part of this equation. So let me not talk about the longitudinal part. All right, then we see right away that the right side would be equal to Q times E prime. E prime, we know this is nothing but this. Gamma E plus V cross B. Transverse part. And now, I remember that the proper time, d tau, is related to the time t for the unemployed frame by this equation. So I can replace d tau by dt over gamma. In that case, then I can dt by gamma is in the denominator, so that this gamma will be promoted to be the numerator, and so that the gamma on the left hand side will cancel the gamma on the right side, so that we are left with b p prime by dt is equal to q gamma scales out e plus v plus b transverse part. But the linear momentum, the transverse part of the linear momentum, which is a vector, of course, is the same in both frames, in both frames of reference frames, the S frame and the S prime frame, just like Y and Z are invariant. They just come from Y, they know nothing. So that, in fact, I can eliminate this one. And this, of course, is the force, the transverse component of the force in with the prime gone in the unprime frame. So that I arrive at the force law, F is equal to Q E plus V plus B. At least that's true for the transverse part. And if you take a look at the longitudinal part, that's still true. Let me remind you that for the longitudinal part, this is completely zero. But actually, what you find is that on the right side, there's only this term. But you can put it in a zero in this form, V cross B. This is the zero. The longitudinal part of this corresponds to zero. So you can put this term in 3 for the longitudinal part. So that, in fact, one can show that this two sides are equal, not only for the transverse components, but for the longitudinal component also. So that we arrive at this expression for the force acting on charge Q in the presence of electric field E and in the presence of electric field B when it moves with velocity V. This, of course, is the Lorentz force law that we're familiar with. So that we have recovered this term in the Lorentz force law, starting from just this term, and then plus our knowledge of special relativity. Wonderful. All right. Now I'm going to go back to take a look at the two second rank and the symmetric tensors that we have introduced so far, F mu nu, and its dual, G mu nu. And last time we saw that the components, individual components of the F mu nu's are given by these two equations, and the components of the G mu nu are given by these two equations. And we saw that if the G mu nu is related to F mu nu very simply by duality transformation. And just as F0I is 1 of C times EI, okay, by duality transformation, you go from F to G, but E goes into CB, so that 1 of C, B as E. Similarly, we can go from this for this spatial component, pure spatial component of Fij, which, by the way, is related to is given by the manifold B with the help of this three-dimensional Levi-Civita symbol, which I hope now you are not afraid of anymore. After all, in fact, you should not be, because Fij is used in vector analysis. Whenever you talk about cross products, in fact, implicitly at least, you are using Fij. Thus, duality transformation goes into that. All right? So both F mu nu and G mu nu are second rank tensor, and therefore they transform just like a second rank tensor as product of two vectors. And so if you know how vectors transform, obviously we know how F and G transform. All right? And I'm done with this. May I erase this? And now make use of this side of the blackboard. To do a couple, at least part of, a couple of problems in Griffith's book. The problems I'm talking about will be problem number 51, and problem 12.47. And I will do part of these two problems for you, so as to familiarize you with these two tensors, F mu nu and G mu nu, to a certain extent. All right? One of the problems in problem 12.51 is to find F mu nu, F mu nu in terms of the electric field E and manifold B. So let's do it. Again, let me remind you, mu and nu are repeating indices. Repeating indices imply summation over 0, 1, 2, 3, independently for both of them. So that I have to list all the possible indices that this product can take. Obviously, mu can be 0. In that case, mu cannot be 0 anymore because of the fact that F is totally antisymmetric. So that we can only take on spatial indices. On the other hand, mu can be take on spatial indices when nu takes on 0 index. So you can have Fi0, Fi0. However, you remember that mu and nu can both take on spatial indices. That's the only thing that's left. Plus Fij, Fij. And Fij, since I and J are spatial indices, without penalty, I can lower it to be downstairs without any penalty. Whereas this F0I has this time index downstairs, so that I can now promote it to the upstairs with the help of a minus sign, F0I. Similarly, here, minus F-I-0. The first term and the second term are actually the same, equal, because I can interchange I0 at the same time. So I0, each time I make a change, interchange I and 0, I have to put a minus sign, but then there are two minus signs. So that minus minus is plus. So this term is same as this term. So that in fact I can forget about this term by putting a factor of 2 in front of it. All right? So then I now have minus 2 times F0I. F0I, of course, is, there's two factors of 1 over 3, so 1 over 3 squared. Then EI. EI, summation over I, of course, is nothing but E squared. Okay? And now, we have to tackle the last term here, Fij. And that's slightly complicated because Fij involves the epsilon ijk. So that I have for this term, epsilon, how come the red colors doesn't come out to be expressed? So epsilon, Fij is epsilon ijk, E, I mean bk. And this Fij is epsilon ij indices are fixed, times, since I've already used k for this part, sum over k is understood. I can no longer use k for this index. So let me use index L. So B L. I can change this ijk to be ijl. And this BL. And this. So that this term will involve epsilon ijk, epsilon ijl, bk, bl. Let me go back and use black chalk. That would be better. All right, let me take a look at the product of two Levi-Civita symbols. So here, ij appears twice, in here and here. So that summation over I, summation over j is understood. But once you have sum over I and sum over j, there are only two indices left in this product, namely k and l. So that this quantity depends on the two indices k and l. So what quantity depends on takes on two indices? Well, obviously, the canonical delta function will do. So that this product is proportional to the canonical delta function of KL, and with assuming multiplicative constants that we have to determine. One can also see that K is equal to L. Why? Because I takes on one value, J takes on another value of 1 to 3. Then what's left would be the third value of 1 to 3. And since I appears in both sides, and both this factor, and J also, so that the remaining index got to be the same. So we arrive at this one. So that this is equal to some multiplicative factor times delta KL. To determine this factor C, all I have to do is to consider a particular value of K and L. So let me consider K equals 3 equals L. in that case, I have epsilon ij3, epsilon ij3. Well, sum over I and j, understood. Well, since 3 is taken off already, so I can only take on the remaining two values, 1 or 2. But when it is 1, then j equal to be 2. And when I is 2, j equal to be 1. So I have only two terms, epsilon 1, 2, 3, epsilon I is 1, j is 2 and 3, plus, okay, I can be 2, j can be 1 and 3, epsilon 2, 1, 3. But these two terms are equal, because I can interchange 1 and 2 to be okay, 1, 2, 3 order. At the same time, I interchange these two to get this. But whenever I interchange this two indices, I go on my side, then it's minus is plus. So in fact, these two terms are equal. 1 and 2. But then you remember that epsilon 1, 2, 3 is plus 1. So the value is 2. Okay? And thus, we are told, is equal to that factor times the delta function of k and L in 3. Delta 3, 3, of course, is 1. This is the definition of conjugate delta. So that we arrive at the conclusion that C is 2. C is 2. Thus, F nu is equal to, I have here already, minus 2 e squared over c squared. And then here we have 2, there's a plus sign, plus 2 delta KL BKBL. Of course, sum over KL. Of course, that will be just B dot B, which of course is B squared. So that I arrive at the result that F nu is equal to 2 E squared minus E squared over C squared. Now I can erase all this and do another calculation. And this time, for what is G mu nu, that is the second part of this problem 12.51. That's easy. Once we have figured out F mu nu, okay, we can go from F mu nu to G mu nu by making the direct transformation. So this is equal to 2. B goes into minus 1 over CE. So this is B squared. So this will be 1 over C squared, E squared. Then minus E goes to B. So it's B squared, C squared cancels. So that will be B squared. So this is equal to that. Finally, the last part of this problem is look at G F mu nu, G mu nu. And I will leave it as an exercise for you to show that it's equal to some factor. I have to do a calculation to know what number this is. And you have E dot B. Exercise. It's done in my lecture notes. I think it's on the last page of the lecture notes I have provided you with. All right? Now, let's do the, I cannot remember. Right, just now. So done 12.51. Now let me talk about problem 12.47. There are 3 parts to this problem. I will do some of them for you. In this problem, we are asked to find out the Lorentz transformation of E dot B. It's simple. E and B, okay, undergo complicated Lorentz transmissions. But their product, here, as you see, corresponds to F mu nu, G mu nu. This is a product of two tensors. And now you remember, just as the product of two vectors remain invariant under Lorentz transmission, product of two tensors remain Lorentz invariant. Therefore, under Lorentz transmission, this will go to F prime mu nu, this G prime mu nu, but that will go into same expression with E dot B. And we are told this F mu nu, G mu nu is equal to F prime mu nu, G prime mu nu because of the fact that product of two tensors will remain invariant, so that we have to conclude that this is equal to that. So that E dot B is in fact E prime dot B, etc. All right? Next, I think the last part of problem 12.47 is the most interesting part. I think it's part C. Let's take a look to see how it goes. All right? Namely that, it is, so this is part A, now part C. So let's be given that B is 0 at point P, but E is not 0 at point P in the unprime frame. The question is, can you find another frame of reference where E, let me call that frame to be E prime, interprime frame. Can you find that frame such that E prime is equal to 0 at the same point, at point P? Can you find S prime frame such that at that point E field is 0? Well, at first sight, it looks complicated. However, we can make use of the following. Let's take a look at this result. F mu nu is given by this. So that we know in the unprime frame, F mu nu is given by 2 times B squared minus B squared over C squared. At point P, B is 0. So that F mu nu is negative. So that since F mu nu is invariant, so that this result, this is equal to F prime mu nu, F prime mu nu, which is equal to 2E B prime squared minus E prime squared over C squared. Now we know this F mu nu is given by negative something. So this is negative. So we are asked whether at that point we can have E being 0. If E was 0, let's turn out there, then this would be necessarily positive. If E prime is 0. But we said that this is equal to that. Whereas this is negative, and now if E prime will be 0, then this is going to be positive. This is negative, this is positive, but they are supposed to be equal. That's impossible. Therefore, no. there exists no frame in which the electric field is zero. At the point where in one frame, in one particular frame, B is zero, but E being non-zero. So that's it. All right. Good progress. And I will need all the backward space I can manage. So let me, in fact, may I erase everything here, because we will no longer need those anymore. So let me erase all that on the backboard. Okay. Now, if you allow me, let me make the following analogy. We have been talking about, given a series of lectures. If we correspond the series of lectures with the different dishes that we order in the restaurant, then we're in luck here because we are finished with the main dish and we are left with dessert. So we're going to have fun. We are going to have fun because, as I promised, we are going to talk about two famous paradoxes that baffled some people when they study special relativity. So paradoxes. I will talk about two. One is known as the twin paradox, which you may have heard of. The other one, I will call it the barn pole paradox. I will tell you what it is. Both are very interesting. Now, let me talk about the twin paradox, and let me use what interesting. Where is the mark? Let's say that we have two brothers who happen to be identical twins. One of them became a physicist, and the other one became an astronaut. And at a certain point in their career, the astronaut brother, the astronaut brother is sent to a distant star or galaxy, and then come back to join his brother on Earth. Of course, the astronaut brother got to take a rocket ship moving at a relatively fast speed to go to the star and come back. But we know that moving clocks run slow. So the physicist's brother, who by the way must have learned special relativity, said that, hey, astronaut brother, your clock runs slow because of time dilation. Moving clocks run slow. So that by the time you come back to join me on Earth, your clock will have registered a smaller amount of time that has elapsed. So that you will look younger than I. Since if your clock runs slow, that means your metabolism rate is low. So that when you come back, I will have aged more than you. Well, the astronaut brother thinks about it and says, wait a minute, if I'm going away in a rocket ship, but except for the small bit of time when I have to turn around from one direction to the other direction, to go from going to the star, to back to the Earth, except for that little bit of the journey when I have to turn to the other traveling in the other direction, I can consider myself being at rest. And you are the one who goes away, then comes back to me. So your clock is a moving clock. Therefore, in fact, your clock should have registered a small amount of time. That will be registered on my clock. So in fact, you should be the brother who would look younger. Well, we all agree that moving clocks run slow. So apparently, there seems to be a paradox. But luckily, it's only a paradox. And there's no conflict, actually, as we'll show. And I will tell you the resolution of the paradox. Why that's so. All right? And it boils down to the application of two things that we know from the study of special relativity, namely the time dilation and length contraction. By the way, it would turn out that the physicist's brother is correct. After all, he's a physicist. All right? For this particular, let me make use of a particular example. So let's say that, I have introduced, you see, I want to introduce two different frames. That's why I have two parts here. That's good. And what is it? So this is, okay, so this is about a new color. Let me consider the situation from the point of view of the rest frame of the physicist's brother. And then we call this the S frame, the unprime frame. In this unprime frame, and I'm going to draw three figures, and this one. So let's draw Earth, and let's see that there's a distant star, and I will assume that the Earth and the star are stationary with respect to each other. So that the S frame is the rest frame for the Earth as well as the star. And let's say that the separation between the Earth and star being 8 light years. That's a distance that it takes light 8 years to travel. And let's say that certain point, brother 2, the astronaut brother, jump on the rocket ship that travels with the speed, let's say from speed 4/5 speed of light. Yes. So then we start with the time being 0 on the rocket ship, and the time registers on the clock of the physicist's brother on Earth is 0. All right? And let me draw the second picture. That will be a picture when the rocket ship carrying the astronaut brother arrived at the star. So this is Earth, and this is star. And the rocket ship arrives. And the time that it will reach will be what? Okay? In this frame, the first leg of the trip, namely for the astronaut brother to go from Earth to the star, I will call it delta T1. the first leg of the trip, would be given by 8 light years traveled with this speed, so it would be 8 would be 8 over 4/5. That would be 10 years. Since the PHYS brother is stationary in this frame, so that means that by the time the rocket ship arrives at the star, the time on Earth would be 10 years. PHYS brother's clock would read 10 years. So what is the reading of the clock on the spaceship? Well, since it is a moving clock, moves with fast speed, and moving clocks run slow, so that what is a slow factor? Well, you remember that you remember this famous right angle triangle, hypotenuse 5, size 4, and 3. So that the famous contraction factor would be square root of 1 minus 4/5 squared, and that would be 3/5. So dilation factor is 3/5, so that if the time is elapsed, 10 years on the clock, on the rocket ship, the reading would be 10 years times 3/5. That would be 6 years. Okay? And then, once the rocket gets to the star, it quickly turns around to go back to Earth. Let's say that the whole trip from one this direction to this direction, well, will take some time. Well, maybe just a matter of hours, and most days, but nothing as big as years. So let's just assume that almost instantaneously, when the clock on the rocket ship is 6 years, it goes back. So at the beginning of the second leg of the trip, the reading of the clock on the rocket is 6 years. And then let's assume that the rocket ship goes back with the same speed with which it had for the first leg of the trip. So it goes with the velocity minus 4/5 minus sign here because of the fact that I'm moving in a negative x direction. The speed is the same, and this distance, of course, as we said, is 8 light years. So that by the time the rocket ship gets back to Earth, this rocket ship travels with this speed, and it has to travel 8 light years, so that it will take another 10 years. So the second leg of the trip takes also 10 years in the S frame, the rest frame of the Earth and star, where the PHYS brother is at rest. So that it takes another 10 years, so that at the beginning of the second leg of the trip, the time reading of the clock on Earth is 10 years. It takes another 10 years for the rocket to get back to Earth, so that the time reading of the clock on Earth would be 10 plus another 10, that would be 20 years. Whereas, the time on the rocket ship upon arrival at Earth would read, when it started with, when it starts the return trip, it's 6 years. But it would take, but there will be another 6 years we have elapsed for the second leg of the trip. Since the time required to take this trip in the S frame is 10 years, But then, of course, this rocket ship travels with this speed, so there is this dilation factor. So 3/5 times 10 is another 6 years. So plus another 6 years. So it's 12 years. So that, whereas the physicist brother will have aged 20 years. The astronaut brother will have aged only 12 years. Therefore, the astronaut brother will look younger than the physicist brother by 8 years. The physicist brother's conclusion was right. And since the reading of the clocks are objective data, so that if the clock, when the two brothers reunite, they can take a look at each other's clock, and both of them have agreed that the clock on Earth is 20 years, whereas the clock that the astronaut brother carries is only 12 years. Those are objective data. Everyone agree with that. So even the astronaut brother will agree. And then the question is, the astronaut brother will ask, where did I go wrong with my reasoning? Since it was my brother that goes away and then comes back to me at high speed. So his clock is a running clock. So that his clock should have read less than my clock. What's the resolution of the paradox? The resolution of the paradox is that the astronaut brother has made one critical mistake. He has been inconsistent. In what way is he inconsistent? The astronaut brother, of course, can move in this direction for the first leg of the trip, but for the second leg of the trip, he goes the opposite direction. He could not be the rest frame in which the astronaut brother finds himself for the leg of the trip is not the same as the rest frame for him for the return trip. So in fact, implicitly, he made a mistake. He had been using, in fact, two different frames to do his calculation. And this is inconsistent. You cannot do the calculations in two different frames and naively get the correct result. Whereas the physicist brother, as shown here, consistently has used, made use of one frame, which is the rest frame he finds himself in, the S frame. So his conclusion got to be right. And to complete the resolution of the paradox, in fact, let us now discuss the whole situation in the rest frame of the rocket ship for the first leg of the trip. So that let me talk about the second frame, which I will call S1 frame. So that this is the rest frame of the rocket ship for the first leg of trip. And obviously, this frame moves with respect to the S frame with a velocity, being plus 4/5 speed, right? That the frame S1 moves with this velocity relative to the unbound frame. Okay? And let me again draw three figures. And I have to be careful to give myself enough space. All right. In this frame, S frame, the rocket ship is at rest for the entire first leg of the trip, while Earth star travels with high speed in the negative direction, travels with minus 4 speed of light, simulated. And now, okay, what is the separation of Earth from star? Since the separation is a moving separation, so it suffers a length contraction factor. Length contraction factor for this speed, of course, is, I think we have just calculated, is 3/5. So that this separation is the rest separation, 8 light years, times this contraction factor. So it is 24/5 light year. That's contracted. All right? Again, at the beginning of the trip, the clock reading on the rocket will be 0, and so is the clock reading on Earth is 0. All right? So then in this frame, okay, Earth goes away from the rocket ship when whereas the star will come towards the rocket ship. Okay. When the star gets to the rocket ship, let me test this second diagram. So Earth will have moved. Okay. So distance already, okay. And this is the star. The star now arrives at the rocket ship. The star moves with the speed 4/5 speed of light. And it has to travel this distance to get to the rocket ship. So how much time will it take? Okay. As observed in this prime frame. So the first leg of the trip in the prime frame is equal to 24/5 times light year. Okay. The distance divided by this speed, 4/5, which is equal to 6 years. All right. Now, so that the rocket ship's clock, since it's at rest in this frame, so we get 6 years. When this star reaches, gets to the rocket ship. All right? So far so good. Whereas the clock on Earth, since it's a moving clock, so that it will have registered, to start with is 0, then the time that we have registered on the clock on Earth would be 6 years times the dilation factor. What's the dilation factor? Well, dilation factor is, again, 3/5. So it's equal to 18/5 years. When the star gets to the rocket ship. Now, the most complicated part of the journey is the rocket ship turns around. The Earth is going far away, going at high speed, so that in order for the rocket ship to get back to Earth, of course, the rocket ship now has to travel at a speed greater than the speed with which the Earth is going away. So the question is, what is this velocity? What is this speed? And we're going to calculate that. But to start with, the clock reading is 6 years. At the beginning of the return trip for the clock on the rocket ship. All right? we assume that in fact this part to go this direction to this direction is negligible compared to the e's. All right. Now let's see. Okay, what is the speed of this rocket ship? In the S frame, the rocket ship speed for the return trip is minus 4/5 speed of light. So what is the speed now? U prime. That would be equal to, well, that's I must have erased it. Yes, I did Einstein's equation. So this is equal to, you remember, U minus V divided by 1 plus U V over C squared. Okay, so U prime is a speed with which this is velocity with which the rocket ship travels in the S prime frame. When we know already that in the S frame it travels with this velocity minus 4/5. So U is minus 4/5 speed of light minus V. V is I'm sorry. Oh, V is 4/5 speed of light also. So minus another 4/5 square divided by 1. Okay, U now is negative. Minus this, and so the V is this, so minus is plus 4/5 squared. And this is equal to minus 8/5 divided by, this one is, let's see, 25 plus 16 is 41 speed of light. So this is equal to, let me simplify. So the U prime, the velocity of the rocket ship for the second leg of the trip will be equal to 5, cancel, 5. So it's minus 40/41 speed of light. So this is U prime is equal to minus 40/41 times speed of light. Which of course, this speed is larger than the speed with which the Earth is gone away. That has to be so in order for this rocket ship to be able to catch up with the Earth. So, all right. So let me draw the last diagram. Now this is the hardest part of the calculation. Let's ask the question: how much time it takes according to building the S prime frame for the rocket ship to catch up with Earth when eventually the rocket ship gets back to Earth? Now, for the rocket ship to get back to Earth, the distance it has to travel is 24/5 light year. And it's going to catch up with Earth, and the catch-up speed is this relative to the speed of Earth. So this is equal to 40/41 speed of light minus the speed with which Earth is gone away, which is 4/5 speed of light, minus 4/5 speed of light. That would be the amount of time according to an observing S prime frame that would have elapsed from for the second leg of trip for the rocket to leave the star and get back to Earth. So what's that? 24/5 divided by, that's this, 41 times 5, and this is, and this is 200 minus, okay, 40, 164, must be right. And this cancel. And this is equal to, okay, 24. Let me do a calculation very quickly. Okay. And light years, that would be years. And 24 divided by, okay, 200 minus this would be 36, 41. 36, okay, 6 would be 6, and no, 4, no, 12, okay, 2, 3. So that would be, okay, 82 over 3 years. So according to, okay, and observe in this one frame, the second leg of the trip takes, okay, 82 years. So far, so good. All right. Now, of course, okay, the clock reading on Earth, okay, to start with, for the second leg of the trip is 18/5 year. Plus the amount of time that you have registered for the second leg of the trip, which is, okay, this 82 over 3. Sorry. Oh, scare me for a moment. Okay. Times, okay, the dilation factor. And, okay, the dilation factor, okay, of course, is, okay, is moving in this S1 frame, let's move with this speed. So the dilation factor would be, okay, yes, 3/5. Which is, okay, lo and behold, 18 plus 82, okay, is 100 divided by 5 is 20 years. So the reading of the clock on Earth, according to the calculation in the S1 frame, in 20 years, by the time the rocket ship, okay, gets back to Earth, which of course is consistent with what we have found 20 years. By considering the situation from the point of view of the S frame. And now the question is, what's the clock reading on the clock by the time it gets back to Earth? Well, for the second leg of the trip, it starts with 6 years. Okay. Then plus, okay, the amount of time that we have elapsed for the second leg of the trip. And for that, okay, we know that in the S1 frame, the time it takes is 82 over 3 times the dilation factor for the clock on the rocket ship. What's the dilation factor? Oh, dilation factor is, well, is the following. Namely that, okay, we see that, okay, the clock on the rocket ship travels with high speed, 40 over 41 speed of light. So that, okay, the dilation factor is 1 minus, okay, 40 divided by 41 square, which we can do the calculation is 9 over 41. Namely that there is a triangle, right, a triangle, with the hypotenuse being 41, with one side 40, and the other side is 9. So that the dilation factor is 9 over 41. 42 divided by 41 is 2. This is, okay, 3. 3 times 2 is 6. 6 plus 6 is 12 years. So that according to the consideration, okay, for an observer in this point frame, okay, the clock reading, okay, on the rocket ship is 12 years. Same as what we found, okay, in, okay, the S-frame. Correct. So there's no inconsistency if you do things consistently and logically. So this is the resolution of the twin paradox. So if you want to age slower, all you have to do is to take a rocket ship traveling a high distance, a high speed, then come back. Just like astronaut brother, for this, in this example, will have aged 8 years less than his twin brother. So this is the first paradox I will talk about. The second paradox is also very interesting. And let me erase others. And look. Okay. This paradox, as the name indicates, involves a barn and a pole. Oh, I can erase this. This is done. Let's say that there's a barn. It has a front door and a back door. One door on each side of the barn. And the barn is, let's say, 30 feet deep. And let's say that there is a pole that is 20 feet long, and there's a fast runner. Let me show this. Holding this rock, this pole. Holding this 20 feet pole. Went from right to left towards the barn, and the barn owner promised to at first the back door of the barn is closed, and the front door is open to let the runner to run through the door towards the back door. So this is the front door. And I'm going to use the following color. I hope it works. So I would use blue color for the front tip of the pole. And I will use green color for the end point of front tip, back tip of the pole, denoted by green color. And I will use black color for the front door and red color for the rear door. So the barn owner asked a fast runner to hold this 20 feet long pole, run very fast towards the barn, and of course this front door is open for the runner and his pole to go into the barn. But since the barn is 30 feet deep, whereas the pole is only 20 feet long, so there will be a short span of time when the pole can be completely inside this barn. So just for fun, the barn owner decides that he will open the back door to let the runner and the pole to go through, just at the time when the front tip gets to the back door. There's no problem. Since once it's open, then the whole thing can go through. So far, so good. And now comes the fun part. So let's say that the runner now is put on the rocket ship. And the rocket ship travels at high speed. And the speed is, the following speed is, of the rocket ship is 99.5 speed of light. Of course, that will give rise to a contraction factor, 1 minus 99% of light will be 99.5% squared. And you can do the calculation. It turns out to be, well, let's just take it to be 1/10. It's very close to 1/10 value. So, okay, let's take a look at the situation as observed by the barn owner. The barn owner says that there is this barn, the front door is here, the back door is here, and I have to use that card sometime. It's very thick. Whereas when now you have the rocket ship travels at this high speed, and the one is supposed to jump on the rocket ship and hold the pole horizontally, just as before. But we now know that since the pole travels with high speed, it shrinks by factor 1/10, so that in fact, let me just draw the pole. So the pole will sunken in to a length 20 feet plus 1/10 will be 2 feet. So this is the pole, 2 feet. And the tip of the front tip of the pole is in green color, in blue color, and the back is in green color. And it travels with high speed. With speed 99.5% square meter. Obviously, since the barn is still 30 feet deep, but suppose now has now shrunk to 2 feet, obviously there will be more time for the short pole to be completely enclosed inside the barn. So the barn owner said, well, I have no reason to change the arrangement. I will, I would have the front door opened, but the window closed. But when, just for fun, when this pole, which is only 2 feet long, has cleared the front door, I will lock the front door. So once the green part has cleared the black part, which is the front door, this door is closed. The back door is still closed. So that, but that's okay, since there will be a certain amount of time when this short pole will be completely inside this barn. And the barn owner promised the runner that when the blue tip, the front tip of the pole gets to the back door, the red part, he would open the back door to let the pole and the runner to go through. So the two events we're interested in would be closing of front door after when the back tip of pole has cleared front door. And this event would be indicated by when the green part gets to the black part, which is the front door. This is event number 1. Let me call it event A. The second event that we like to compare this event A with event B. This would be the opening of back door. When front tip of pole gets to back door. Let's talk about the situation in two different frames. The first frame is the bound frame. The definition is a frame in which the bond is at rest. And I'm now going to solve this paradox, which I'm going to tell you, okay, in a moment, by graphical means. I'm not going to do any calculations. I'm just going to draw diagrams. So that what I'm interested in would be the following, namely that I'm going to draw space-time diagram. One in the bond frame and the other one in the rocket frame. And let me indicate, so in this frame, it is customary in the study of special relativity to plot time vertically or space horizontally. So let's draw time. Oh, be careful. Since I use color, big color. So let me draw the trajectory of the front door, by means of black color. Okay, so that is a vertical line. Since I have space horizontally and time vertically. So this would be the trajectory of the front door. It's a vertical line. And I will use the blue red color for the back door. And this is 30 feet deep. All right? And now, we have in this frame, the pole is very short. So let me draw the trajectory of the two ends of the pole. So when it gets to this, and let's say that when the tip goes, front tip gets to the back door. So let me now, let me choose the coordinate of space and time. X, to be such that a beam of light being sent from this to the right will travel at with this trajectory, which is 45 degrees with respect to both the time axis and the x direction and the space coordinate. So I just choose to use it that way for convenience. So that for particles traveling with a speed less than the speed of light c, remember stationary objects, the trajectory would be the same location for all the time. So be a vertical line. So that for an object traveling with speed less than the speed of light, and this all this allowed, the trajectory would be in fact less than 45 degrees with respect to the time axis. So we would be going, for example, for the with the blue color for the tip, front tip of the pole. It will travel with a trajectory which is less than 45 degrees. So that thus the front part will travel with speed with trajectory like this, and the trajectory for the back part of the pole would be parallel to this same speed. Not too good. Anyway, this should be enough. So there are two events that we're interested in. Event A is the closing of the front door. The front door is here. It closes when the back tip of the door is clear. So this is event A. And the second event is when the front tip, this gets to the back door. So it's this. So it's the one event B. corresponds to the intersection of the blue line and the red line. So this is blue. And this is time. So you see that the barn owner is correct. Okay. For a short period of time, the pole would be completely inside the barn. And in this frame, event B, event A, event B is after event A. Okay? So far, so good. And now, let's look at the situation from the point of view of the rest frame of this rocket ship when it travels at this high speed. Okay. Rocket. Okay. So I will call that the pole frame. In the pole frame, of course, okay, it is the barn which is moving high speed towards the pole. With speed, 99.5% speed of light. So that the barn suffers a Lorentz contraction from 30 feet to 30 feet times 1/10 will be 3 feet. So according to observing in the pole frame, the barn would be only 3 feet deep. So let me tell you, the front door and then the back door will be only 3 feet deep. Whereas, of course, the pole will still be 20 feet long. So this 20 feet long. It is the door, the barn which is moving with high speed towards the pole with speed of 99.5% speed of light. Now, you can see that obviously, according to the people observer in the pole frame, the length of the pole is bigger than the depth of the barn. So how is it possible for the barn to hold this pole inside the barn? In particular, obviously, it looks like disaster is in the making. Especially when you remember that the barn owner is going to open the back door after the closing of the front door. So obviously, it looks like that there is going to be a disaster. And, well, obviously, either the rocket ship and the runner would meet the dune, crash into the barn, or nothing will happen, really, and they would, the whole thing would go safely through the barn, as the barn owner would believe. And the question is, who's right? Of course, if you have this conclusion, it seems to be logical, and that conclusion can be checked by seeing whether the rocket ship and the runner would be killed or destroyed or not. And those are objective data. Everyone should agree. So that we would expect that, in fact, even people in the barn frame would find out that, in fact, nothing spectacular will happen. And that the pole and the runner would pass through the barn safely. And the question is, how is that possible? All right, again, I'm going to draw my space-time diagram now in the pole, and I'll draw the trajectory of the pole since the pole is at rest. And the front tip of the pole is blue color. So this is the trajectory of the front tip of the pole, and the back tip is this green line, and they're separated by 20 feet. and it is the barn, which is only 3 feet deep, would be running towards the pole. And so let me draw a trajectory. And it will travel speed very high, but less than the speed of light. So let me draw the trajectory for the front door in black color. And it is 3 feet. That is the front door, and the back door is in red. This would be the trajectory of the back door, and this trajectory for the front door. This is trajectory in the space-time diagram for the front tip of the pole, and this one corresponds to the back tip of the pole. And you remember, event A corresponds to the clearing of the pole at the front door. So that it corresponds to the intersection of black trajectory and green trajectory. Green and red, so this is the event, which we call A. Green and black meet at this point A. Whereas the second event, which is the opening of the back door, corresponds to the intersection of these two trajectories. Red and blue. Red and blue. Red and blue is here. So this is event B. So that according to the people in the pole frame, B is before A. Whereas in the barn frame, B is after A. So the chronological order of the two events got reversed in this example. So that according to the view in the pole frame, what happens is that the barn owner opens the back door before he closes the front door. See, time goes vertically. So this before that, whereas here is the other way around, this before that. So that the chronological order of the two events got reversed, as observed in the two different frames. So not only is simultaneity relative, even the chronological order is relative in spatial relativity for events like this. So this is the resolution of the pole barn paradox. So that in fact there's no disaster, as the barn owner has been insisting to be the case. And then, of course, now the one has agreed. In fact, nothing bad happens to him. So that is it. This is all I want to talk about for the two paradoxes. And also, well, this is the end of the last lecture for this course. And since this last lecture, I would like to say a few words to those of you who will be leaving UNC right after this semester, especially those who are international students. I'm so sorry that the coronavirus outbreak has taken place just before we are about to leave. I realized that the pandemic has caused you great inconvenience and possibly even great misery. But I do hope that you will not let yourself to think that you will not let yourself to let this pandemic to cast a dark shadow in your memory of UNC. I hope that we have a fond memory of Chapel Hill. And now I would like to say goodbye to you. with the aid of a poem written by Thomas Wolfe, who graduated exactly 1 century before from this very university. I will take the liberty of making slight modification to his poem so as to reflect our warm wishes to you. Here goes. Sometime when the springtime comes and the shifting moonlight falls, we hope you'll think again of your time here and of these old-brown walls, of white old Wales and of Old South, with bells deep booming tone. We pray that you'll think again of Chapel Hill and, thinking, come back home. I bid you a fond farewell. So long. Thank you.